Hello, good afternoon, everyone. So today we'll talk about sensitivity and uncertainty analysis. This will be an extension of a lot of the stuff that we've already been discussing, but I think is one of the sort of crucial elements of doing any modeling or systems-based analysis. The world in which we work in has a lot of uncertainty and parameters and in knowledge about, specific variables or inputs into the model. And so you need to be able to incorporate these sorts of methods in order to really sort of have any robust confidence in a set of results. So I will start out with a fairly simple example here. And I'm going to ask for a volunteer once again to help me out. Anyone want to lend me some of your knowledge?
You can go ahead.
All right, Trisha. So this is a plot of life cycle emissions, which means kind of the emissions from cradle to grave of, in this case, using conventional gas versus unconventional gas. So what can you tell me about conventional gas versus unconventional gas, just looking at this chart right here?
It looks like conventional gas has lower emissions.
Okay.
In terms of CO2, grams of CO2 equivalent.
Yep. So not a trick question or anything. That's kind of intuitively obvious from looking at this. You would say, okay, I'm basically comparing these two things and one looks like it's lower than the other. Okay, so let me go to the next slide. Okay, so why don't you reinterpret your results here?
Okay, unconventional gas has a wide range, perhaps, of life cycle emissions, and so it can be worse or much better than conventional gas.
Yep. And so we don't actually know anything about like how that bar is distributed and how likely any outcome is, but now you're basically saying, there's some chance that it can be better, right? How about now? Does what would you say about this graph?
It's a little confusing. If the blue was saying like average or median, then conventional gas probably has. It's tricky to say. I guess the variation is conventional gas can get much worse than unconventional.
Yep. Exactly. And what would something like this tell you?
That conventional gas is much better on a life cycle emissions basis.
Yeah, exactly. And now, like, if this were to actually represent the real range, right, then you have a lot more confidence in saying one result is better, quote unquote, better than the other, compared to something that's just blank like this, right? And so okay, so thank you for volunteering here. And so the point of this example is really to show that including the uncertainty analysis can really be important in having your audience interpret the results correctly. And even I would go so far as to say that not including uncertainty or sensitivity analysis, especially when you know that sort of thing is prevalent, is actually very deceptive. And I actually use this particular example because it's something that I saw in person. I was in a conference in Europe when I was in grad school, and this executive from ExxonMobil was giving a speech about the emissions coming from conventional gas and unconventional gas, and they cited this one paper that happened to be a professor from the same university that I was going to at grad school. And that speaker actually photoshopped out the uncertainty bars, and it totally changed the perception of how you would interpret the emissions impacts. And so in this particular case, I went and talked to the professor who had written that study, and they were basically outraged that someone could manipulate the results like that, and it really kind of demonstrates the importance of being able to think about these uncertainties in displaying your results and getting the audience to have a different perception of what it means when you do include uncertainty in your results. Okay, so uncertainty, this is the lack of certainty, a state of having limited knowledge where it's impossible to exactly describe existing state or future outcomes, right? Basically, if there is something unknown about some state of knowledge, then that means you have less confidence about in any one particular set of results. There's this famous quote from Donald Rumsfeld that I think is a nice kind of breakdown of different sort of types of uncertainties. So I just tried to highlight that here. So there are things that are known knowns, so things that we know. There are known unknowns, which are things that we know that we don't know. And then there are unknown unknowns, right, which are things that we don't even know about that could affect the results or outcomes. And those are traditionally kind of like the hardest types of things to really account for. And so when we talk about sensitivity analysis and doing scenario analysis and deeper sort of uncertainty, a lot of the stuff that you try to incorporate into analysis are things that are kind of known unknowns. In other words, things that I can imagine that sort of encompass uncertainties that I know about the system. But you should always keep in mind that there's this lurking unknown unknowns, which are basically things that you can't really account for in the modeling. And that's not something that I have really good advice in solving this issue, right? Because it'll be very case specific, and by nature, it's hard to basically address those types of issues. So we'll mainly be focusing on the known unknowns rather than the unknown unknowns. Just remember that sort of thing is often present in your analyses. Okay, so what we'll talk about today is going through a series of logical steps in breaking down uncertainty that gets introduced into your analysis. And so we'll go through all of these. So the first one is known as sensitivity or scenario analysis, or some people even call it what if analysis. And essentially what this is when you compute the effect of a single change or a single set of changes in the inputs on the outcome of your model. And so you can imagine that you build some kind of model and it has a bunch of inputs, and maybe you have some kind of base set of values for individual inputs, but then you know that some of those inputs can vary. And so this is a way of being able to investigate that. And it's particularly nice at identifying factors that are really influential in the model. And we'll show a couple examples of that in a second. Uncertainty propagation. So this is calculating the uncertainty in the model outputs that are a result of your input uncertainty. And so this is closely sort of tied to the first one. And then there's this sort of broader uncertainty analysis, which is comparing importance of input uncertainties in terms of their relative contributions to uncertainty in the outputs. And this sort of broader example is one way in which you can look at kind of the distribution of outcomes as a result, following from individual uncertainties, variable uncertainties. All right. So the first example that we'll talk about is tornado diagrams. So this is often a good way of doing one-way sensitivity analysis. So one-way sensitivity is where you make a graph that essentially varies a single variable from what you know about it, from like a low to high and range, and then you can show the output as a function of that specific variable. One of the common ways to show this is known as a tornado diagram. There are other ways as well. You may have heard of things like spider plots. But I'll just be showing this particular example where you look at many sort of one-way plots on a single chart. And we'll show this in a second. So the main idea is if you have some kind of function, right, with a couple inputs like x1, x2, and this can go on to have as many sort of inputs as you want. The basic question is what happens to your outcome, y, as you vary each of your variables individually, so x1 and x2 and so on and so forth. Okay, so let's take a look at an example by revisiting one of the decision tree models that we reviewed from last class. So the Pennzoil court case. So this is the tree that was drawn just as a quick refresher, right? You have this court case going on, and you've got a decision to accept a settlement agreement or accept or reject the counter offer or counter offer. And then these are kind of your outcomes. So then how might the decision for both of these things, so you've got your two decision nodes, one thing that we might want to investigate is what happens if the outcomes are different. So if the expected values of our decisions shift, if the payoffs are different, and even you could even shift, for example, probabilities of particular outcomes and seeing how that would affect, how that might affect the outcome as well. And then the other thing is that we would be able to look at which parameters have the largest effect on expected values. So in this particular case, let's take a look at what happens if I just kind of shift all of my different payouts, right? And so there's this question of like, okay, if I were to change any sort of one of these values, you know, maybe I add like $1 million into each one. So the actual like expected value change is not going to be the same because you're multiplying across these different probabilities, right? And so changing certain elements may have non-straightforward impacts on your outcomes. And we're able to look at this. So this is a really sort of simple example of a tornado diagram. So in this case, what we're doing is we are varying each of these parameters by plus or minus 50%, and that particular choice is kind of arbitrary, but you can imagine in a real world example where you actually have a good sense of how much a particular parameter can vary. You know, you would just do it by the sort of low and high end of what you can imagine there. And then these are typically ordered by the largest influence to the smallest influence. And so that's where the tornado diagram name comes from, because the actual graph ends up looking sort of like a tornado. And you can see, for example, in my expected value of refusing a particular decision, the win small parameter ends up being the most important. So if I go back here really quick, it turns out that this parameter of that I'm calling win small is the one that's going to be having the largest effect on the expected value. And that can be kind of intuitive in this case because you know, it's got the largest probability. So the weighting of a single dollar, of a marginal dollar change in that parameter is the one that's going to affect your expected value the most. But you can imagine that you may have like a more complex model or a complex function where it's not so intuitive. And being able to just pass in these values and figure out the outcome and then measure and graph it like this is a really sort of clean, simple way of being able to quickly be able to say, hey, this thing is going to make the sort of largest influence. Okay, any questions so far about this? Hopefully this is not confusing anyone too much. All right. Oh, wait, I see someone.
Sorry. I was just on a tornado diagram like this, if you were to vary each input by a different amount, would you still use this kind of a diagram, just basing it on like the possible variance within each one, and then just saying, well, this is the expected variance within this one, within all of them, and they're all different, but we can still put them in this sort of comparative?
Yeah, that's a really good question. A lot of the tornado diagrams that I typically see do this kind of thing where it's always like plus or minus some amount of value. But what you're suggesting, which is to say that like the variation that you see in one variable may be different from another one, I think that's totally fine to do it in this format. You just need to be careful in the explanation and interpretation of the results, where you say, instead of saying like, oh, we varied all the values by some percentage, you can say we looked at the sort of range of possible values, right, and put those differently for individual variables. And so then the interpretation of the tornado diagram becomes more like based on the range of values that we're putting in, these are the most important variables. And actually that way probably makes a lot more sense than in this one, because you have you probably have some confidence in that range of values, as opposed to here where we're just saying, if they're all sort of weighted equally. Yeah, and so the interpretation would be slightly different between those tornado diagrams, but it would be perfectly valid to have different ranges for the variables. Yeah. Okay. So this, again, this type of approach is really nice in able to really sort of pinpoint the sort of individual effect, and it doesn't, again, this doesn't have to be just applied to like a decision tree. Basically any model that you have like sets of inputs and then an output, this is a type of a useful approach to figure out like the most influential variables. One sort of drawback of this type of approach is that maybe you have some question about like a nonlinear relationship between two variables, right? And because this is like a one-way sensitivity where you're looking at only sort of one item at a time, you run into you may run into this problem where you're not actually able to observe relationships happening between multiple variables. And so that's where we start to build in more complexity into the sensitivity analysis. But again, even a one-way sensitivity, I think, does a really sort of nice job at any sort of single variable analysis. So the next step, maybe this is intuitively obvious, but the one way you could approach this is to do a two-way sensitivity. And so let's say we wanted to look at the variable win big and how it interacts with the accept Texaco counteroffer. And so what happens if I vary the win big payoff versus the accept Texaco counteroffer payoff at the same time? And so it's kind of like a tornado diagram, but now I actually have to look at a whole series of values, right? Instead of just looking at the high and low for one variable, I'm essentially going to say, okay, what if I do the low of one variable versus the low of another variable, or low and then medium and then low and high, and doing all of those combinations. And that gives you this sort of map of what your, for example, in this case, what your outcome or your expected value might be. So the logical extension of this is the ability to kind of do this for as many variables as you want. And so there is actually a technique that we're going to talk about in just a bit that will let you do that. But in this context, there's a particular difficulty with like going from a two-way sensitivity to like a three-way or a four-way sensitivity, in that you're basically adding these dimensions, but it becomes really difficult to properly visualize what that outcome looks like. And so usually when you're doing this sort of sensitivity analysis for specific variables, you're not typically going to go beyond two-way sensitivities, and that's mainly for, again, because of the drawback for visualization. Okay, so let's take a look at what this looks like. So again, keep in mind you've got your win big and your accept Texaco counteroffer payoffs, and those are the outcomes that we are varying. Okay, and so the expected value for that particular decision, it looks something like this as I change my two parameters. And so you can see, right, I'm just picking a range of values to vary by, and you can see how the EV of my decision is going to essentially change across all of the values. And so instead of like the tornado diagram where you just have the sort of high and low, now I have the map of all of the values as a function of two particular variables. And then I can actually remember that the decision-making process hinges entirely on, you know, when you have a higher expected value in one decision branch versus another. And so I can actually extend this to really discretely look at how my decision-making process might change. Okay, and so in this case, this is the same two-way sensitivity, but instead of looking at the overall expected value of your outcome, now I'm basically measuring out the EV of the two branches for each decision. I have my first decision about accepting or declining the first offer, and then the second decision about accepting or declining the second offer. And you can see, right, that there is a sort of decision space in which, you know, if my, if the payoff were, you know, negative for the court award, for some hypothetical reason, right? These are kind of just made up numbers. Or if it's below, you know, 2.5 billion in the counter offer, right? There is a world in which I would accept the first offer rather than decline it. And so this is a nice kind of map. You can imagine, like in a real world situation, like, okay, you make this decision tree and then you just say, oh, yes or no, we're going to do this decision versus this decision. But if you have any uncertainty about the payoffs, which you probably do, or uncertainty in like the probability of outcome or something like that, you can do this type of analysis to show, hey, like, maybe in a lot of cases, we would always sort of decline, right? And it's really robust to your decision-making process across a wide variety of parameters, because you might say like, oh, the chances that it's going to be in this range is really small. But then, or you could show in the second decision, for example, that like your decision about accepting or declining is actually fairly sensitive to, you know, the range of possible values. And so this really kind of harkens back to that first example I was showing, right, where, you know, when you have the bars with and without the uncertainty or error bars, then that can really change your sort of perception and like confidence in a particular set of results. And so contrary to last lecture where we just calculated the EVs and we said this decision or this decision, you know, now that you've done some sensitivity analysis, I can now be more or less confident about a particular decision. Okay. Any questions about the one-way or two-way sensitivity? right. Let's show another quick example. So again, going back to our insurance example from the end of class in last lecture. Again, you can do variation on specific parameters. And this time, we're actually going to change not just the payoffs or an expected payoffs, but you can also change the rates of a particular incident happening. So in this case, what would happen if we change the rate of accidents, and then what happens if we change, okay, one of the payoffs, like the amount of damage. So in this case, what happens if we change these parameters, the $800 damage or the probability of the accident happening. You can also look at what happens if you change the type of person making the decision, right? In this particular example, this function with u equals 10w to the 0.3, that is an example of a risk-averse person. What happens, if we change it to someone who is risk-neutral versus risk-seeking? How might that change? So if you change these parameters, for example, how does the insurance rate change? What happens to the profit of the insurer? So let's start off with doing a one-way sensitivity on each of these parameters. Okay, this plot isn't actually arranged in a tornado, but just imagine that like these two went below, and then you've got your sort of largest to smallest. Again, in this case, we're doing a variation of plus or minus 50% from the value. Turns out that like the utility constant, in other words, this value, this 10 value here, doesn't actually have an effect on the insurance amount that should change, or on the profit that the insurance companies would make. And the cost is important, but the most sensitive parameter is the probability of the accident actually occurring. And again, like in this kind of simple example, it's somewhat intuitive because you can go back and kind of figure out the relative weighting on your outcome just by the like magnitude of your particular parameter. But again, in more complex examples, you wouldn't be able to do something like that. And even then, like kind of just looking at the structure of this problem, it's not immediately intuitive to me that like changing this P is more important than changing the damages or changing these items, right? But from the one-way sensitivity, again, it's like a nice single variable variation that is a fairly simple and straightforward way of being able to figure out which variable is the most influential in the outcome of your model. I would say it's not so intuitive just by looking at it, but by doing this analysis, you can really quickly identify the most important variables. So I'll quickly note that all of these particular plots and diagrams and this one-way and two-way sensitivity analyses that I showed in these two examples, I implemented all of that stuff in R. You don't have to use R to do this. You can do it in Excel or another programming language, as long as you kind of understand the core principle of how to essentially put together the formulation and then vary the inputs. But I will say that in addition to the lecture notes that are put on Canvas, I also put the code that I used in R. I can just really quickly sort of show that here, which goes over essentially how I did all of that. And those are contained in these sort of functions that are testing your one-way sensitivity or are just like building the model. So I'm not going to go through this, right? It's specific to that programming language, but it is posted online so that if you want to take a look at it, you should be able, hopefully, to decipher the code to see exactly how I implemented these sensitivity analyses. Okay. So any questions about these one-way and two-way sensitivities? Actually, why don't today's lecture might be a little bit shorter. So let's take a break right now and we'll do the same sort of same deal as before. We'll take a 5-minute break and I'll answer any questions anyone has in the meantime. All right, so let's continue onwards. So the next sort of logical extension about this goes back to what I was talking about in terms of extending the sensitivity analysis to multiple variables as opposed to doing them sort of just one by one. You know, you could imagine a world in which you have many different variables that all kind of interact with each other in different ways and could lead to really sort of nonlinear outcomes, in which case, you know, doing a one-way sensitivity may not be a really good representation of the uncertainty, particularly because uncertainty in multiple variables can lead to outcomes that aren't really nicely captured by, you know, these tornado diagrams, or even in the two-way sensitivity like mapping. The other thing, right, is that in a tornado diagram, you're basically looking at the range, at the sort of largest change in outcome based off the range of the values. But it doesn't really tell you anything about what's going on between your low and high. And even in the two-way sensitivity, okay, yes, you are looking over a sort of full range, but you don't know anything about how likely one particular outcome is. So in this type of sensitivity analysis, the certainty of a value of a particular input is not well captured. And so one of the sort of most common approaches to deal with this, with both of these problems, is known as Monte Carlo analysis, which is a really nice way of doing uncertainty analysis, particularly across uncertainty through multiple variables. And there's definitely some trade-offs between doing a full-blown Monte Carlo versus doing these one-way or two-way sensitivities. But sort of together, they give you a nice holistic view of the uncertainty that sort of propagates in your inputs and what it means for your outputs. So let's talk about how Monte Carlo works. This is like a super simple diagram of what's going on in a Monte Carlo. Imagine in this particular case that each of these distributions on the left represent some kind of input distribution. So for example, this might be like C1, C2, C3. These might be like your cost outcomes for like the payoff in the previous examples, right? So it could be something like this, and in which case, instead of just saying a low and high value, you actually know kind of what's going on in the actual distribution. And then the iterative assembly function is just whatever algorithm is being used to calculate your outcome. And so, what ours was something like EV is equal to, probability of 1 times C1 plus probability 2 C2, something like that, right? And so this could be your iterative assembly function for this particular example. And so essentially what you're doing is you calculate this value. Let's say that you pick a single value here, a value here, and a value here, and that's going to lead to a particular EV outcome. And maybe that is something like, that's your one example. And then you sample from these distributions again, and maybe you end up getting a sample there and a sample there, and maybe a sample there. And then your next outcome looks something like this. And you continue to do this over and over again until you have a distribution of outcomes that is represented by this final distribution here. And so when I look at this result, it is giving me this a distribution of results that represents, based on what I know about my inputs, how likely any particular outcome will be. And so this is less able to describe the influence of single variables as you would be able to see in like a one-way or two-way sensitivity, but instead it will give you kind of the full range and likelihood of outcomes based off of what you know about all of the inputs. So it's a pretty handy technique that will let you complement the sensitivity analysis with more knowledge about uncertainty across all of the outcomes and the likelihood of any particular outcome. Okay. So Monte Carlo comes from, it's essentially a way of doing statistical sampling. It originated from the Manhattan Project actually in the 1940s. And essentially we're doing many iterations of picking inputs to generate a distribution of answers. So basically what I had just described, and to maybe formalize the steps a little bit, the way this works is, so one, we specify the probability distributions for your uncertain variables. This one is particularly tricky in application because it often means you need, or oftentimes the sort of best ways of doing this is essentially getting good data. But in the absence of good data, there are still ways to get at reasonable distributions for variables, even if you don't have like parameters about what the distribution looks like. So like if you were doing like a normal distribution, you'd need like the mean and standard deviation and that sort of thing. But even having something like a high and low value, or like which would be a uniform distribution, or a high and low value and a most likely value, which you could turn into like a triangular distribution. These are all simple ways of turning knowledge about your variables into distributions that could be used in a Monte Carlo. Okay, and then the second step is, once I've built the distributions for all of my input values that I want to investigate, I then randomly sample values from that distribution. You then calculate the model output for each set of samples, and you iterate this again and again until you've built out a smooth output distribution that you then have a lot of confidence represents the sort of possible avenue of outcomes based on what you know about the inputs. Again, the Monte Carlo doesn't produce this like one number or answer, right? It makes a distribution of results that you can then interpret in a variety of ways to figure out what you want to say about your outcome. Okay, so I want to take a quick aside to talk about one of the most famous examples of Monte Carlo. This is kind of just to highlight the sort of power of doing the Monte Carlo and show kind of a unique application of it. Not really directly related to energy modeling, but that's all right. Okay, so probably the like quintessential example that is taught about Monte Carlo is calculating a value for pi. So calculating pi. So the main idea is how I can relate random draws into something about a parameter of a circle, right? And so one of the ways that people talk about this is, okay, let's draw a square. This is a terrible square, 1 second. That wasn't much better, but that's all right. Okay, so let's draw a square, and let's just say that the length and width are equal to 1. And then let's draw a terrible circle. I'm a lot better at doing this on the whiteboard. Let's see. So what do I know about this circle? So the circle itself is contained within the square where your edges are connecting here, which means that I know the diameter is equal to 1. And so one of the things that I can calculate is the area of the square, which is equal to my length times width, which is just 1 times 1, which is equal to 1. I also know the area of this circle. Area of the circle is equal to pi r squared. And I know that the radius is equal to 1/2, right? And so this is pi times 1/2 squared, which is equal to pi over 4. And so I can solve for pi as a function of these parameters, which is equal to 4 times the area of my circle over the area of the square. So once I get to here, I can know something interesting about this property between the circle and the square, which is a direct relationship between the areas. Okay, and so how would I go about taking advantage of this in the context of sampling? And so one of the ways that this is commonly taught is they describe this example as like if you were out in the wilderness and you had to figure out the value of pi, you know, how could you do it with this method? And the way that you could replicate the sampling is, okay, let's suppose that I draw out the square and the circle on the floor. You could take a bunch of rocks, for example, and then throw them into this area. And eventually, let's say anything that lands in the circle is going to be, you know, red, and anything that lands outside of the circle is going to be blue. And if I throw enough rocks into this area, the count of the points within the circle and the points within the square are going to be representing the area of your circle and the area of your square. So what I can do is I can choose, so in a Monte Carlo, right, I can do a PDF where I go from 0 to 1 for x. So this is my x value, and I can do the same thing for y, 0 to 1 for my y. And I can now take these distributions as my input distributions and randomly sample from these guys. And I know, right, that that I can then essentially use this Monte Carlo in order to simulate the values of these x's. And if I do this enough times, then actually the closer and closer I'll get to replicating the actual values of the areas. And I can just use this simple equation here to calculate pi. So this is a sort of famous example of that, and I'll just kind of quickly show this in code to show how this works. Okay, let me clear the board here. All right. So this is a two-function Monte Carlo example. So I've got these two functions here. And again, you don't need to know all the syntax and everything that's going on, but I'll kind of walk through this so that everyone can see what's happening here. So there's a function called RUnif, which stands for random uniform. So this is drawing from a random uniform distribution, and I'm going to take one draw from it, and it's going to be between 0 and 1. So just to show you what happens if you just run this function, right? It's just going to give you a random value that is in between 0 and 1. And it's going to do that for both x and y. And then it's going to calculate this value that is basically going to say, okay, if it's within x squared plus y squared to the 0.5 is less than or equal to 1, I'm going to assign a value of 1, otherwise that's 0. So what this pi calculation does, calculation. So what this function does essentially is it throws one rock into that space, and if it lands in the circle, it's a 1, and if it lands outside of the circle in the square, then it's a 0. So I could do this many times, right? And eventually, if you throw enough stones into that area, then you'll start to get some examples where it lands in the square but not in the circle, and that's all this pi calculation does. It's essentially one stone throw. And then the Monte Carlo is basically saying, okay, I'm going to do that many times, and then I'm just going to do that equation 4 times the number of times that it lands in the number of times that it lands in the circle versus the number of throws that I made, which represents everything, the area of the square, right? And so let's take a look at this. So if I do 4 times the ratio between the number of times it lands in the circle versus the number of times it lands in the square, let's say we do that 10 times, you get a value of 2.8. And if you do it multiple times, right, you're going to get different values because these are randomly drawn simulations. And throwing that rock in, it may or may not land in that space. Okay, and so if I do it 100 times, I end up getting some of these values. If you do it, let's say 1,000 times, right, you start getting closer and closer. And so with enough sort of repeated values, you end up getting the ability to simulate values that are relatively close to pi. Let's see what happens if I do it. What is this, like 10 million times? Might take a little while to run that simulation, but yeah. And so, yeah, there you have it. It's a nice little small example of a famous application of a Monte Carlo, where you essentially your inputs are your x and your y, and they're just created as uniform distributions. Okay. Any questions about that particular example? I do have one sort of slide on that and kind of describing how that works.
In your code there, you were just looking at like one quadrant, the top right quadrant, correct? And because it's all like symmetrical.
Yes.
Instead of like a whole circle. Okay.
Yeah. Yeah. Good catch, because it's the x squared plus y squared. I'm not doing all sides, but yeah, it ends up being the same because it's all symmetrical. Okay. So going back to a little bit of the discussion about thinking about the distribution for your values, this can be one of the sort of harder things to do when you're actually implementing this in reality, in like your research, for example. Think really carefully about choosing the distribution and its parameters. Like, do you even need a distribution at the end of the day? Okay, and then there are a couple of different types of distributions that are really common in these sorts of analyses. And that has to do a lot with the fact that they're fairly simple and straightforward, which means that the implementation doesn't need to be extremely complex when it comes to trying to figure out what to assign into your as the distributions representing your parameters. So there are discrete distributions. So binomial distribution, for example, yes or no outcomes. This could be, like a coin flip type thing. It doesn't always have to be 50-50, right? You can weight it to be yes or no in one with a particular weight. There's also Poisson distributions. So this is the probability a number of events occur over a period of time. So this is really common to represent extreme events. And so, for example, you could do Monte Carlo simulations of for example, like damage from an earthquake or damages from like tornadoes or hurricanes, for example. And it's not as though you have like the same probability of a disaster happening every year. Instead, it sort of describes how many events of extreme events might happen over a long period of time. So that is one common distribution type that is used to represent extreme events. Then you've got continuous distributions, normal distribution. I think most people know about this. It sort of describes a symmetrical distribution with some likelihood that particular events happen based on the standard deviation from the mean. A log normal distribution is really common as well. And these are typically to represent inputs that are similar to normal distributions, but usually take on positive values. And that's because you can't have negative values for log normal distributions. And so, if you're doing like for example, like, okay, one example that's coming straight to the top of my mind is if you're modeling like the sales of like cars. Okay, and you know, I work in transportation, so it's not unusual to model something like that. You can't have like negative sales of vehicles, and so when we represent the distribution of sales, you might apply a log normal distribution because it looks like a normal distribution, but we don't want it to go below 0. And then probably the two most common are going to be your triangular distribution and uniform distribution. So this is like if I know the min, max, and most likely outcome, or the most likely value for an input, then you can build a triangular distribution with the min and max being the bottom of the triangle and the most likely point being, you know, the apex of the triangle. And then a uniform distribution, if you really don't know anything about what values it can take on besides the min and max, right? You only know the range, then that's a common distribution to use. So this is going back to our original example in the decision tree with Pennzoil. So in the one-way sensitivity, we looked at a series of 5 different variables. So accepting the offer, making a counter offer, the win big, the win small, accept technical counter offer. So in this case, I just applied a whole bunch of random distributions. I just selected a couple to show what a Monte Carlo would look like in that case. And so in this example, we see a 2 normal distributions, okay, and that's the accept offer and accept counter offer. I have 1 triangular distribution, looks something like this, and then a win big. And so these are all just showing random draws. So this is like 10,000 random draws, and it shows the values that are essentially getting selected as I go through my sort of first and second Monte Carlo steps. Yeah, and so if I then sort of go through the expected values of each of the decisions, I can sort of slowly compile as I do draws from these distributions, the value of each of my expected value outcomes. And so that ends up looking something like this. So here I have in red and in orange the accept your first and second offer. Okay, and so I'll quickly say that this is like a really typical sort of example that you'll, or example result that you'll see from the Monte Carlo analysis is like a series of different distributions of outcomes. So the expected value outcomes for accepting the first offer and accepting this, or declining the first offer, so that's this red versus green, looks something like this. And then in the blue and orange is accepting or declining the second offer. So this is really where it comes down, like this is where you see some of the value of the Monte Carlo analysis. I'm able to really observe what the distributions of my outcomes look like, the range of values and the range of likelihood of particular values that I'm going to see in a particular outcome. In this case, I can see that like the green distribution is pretty often quite a bit larger than the red distribution, right? Which means that I'm I'm more inclined to sort of decline the first offer. And really, there are some instances, right, where the red can be higher than the green, but you also have to take note that like some of those values can be correlated. So you may or may not necessarily ever be able to get a result where the green is actually lower than the red. And I'll show an example of how to think about in a moment. But even if you were, right, to think about that, you could say that, hey, like it's only in, say, the bottom, 10th percentile of the green and the top like 15th percentile or something of the red, where you would actually change that decision. And so you might say, I'm fairly confident that like 80% of the time, 85% of the time, we really should be declining the first offer and versus accepting the first offer. And you can see that like qualitative decision-making process, it could be really different, right? If the distributions may look something like this, with the orange and the red, where there's a lot more overlap, and you might say, oh, but if we get to the second offer, I'm a lot less certain about the expected value being better one way or the other. So there is an additional sort of principle to consider with these outcomes. It's like I was saying, because the outcomes are correlated with each other in certain ways, right? Because the expected value is based off of calculations on parameters that may overlap, may be present in both of the EV calculations. And so the stochastic dominance is a nice way of kind of being able to back that out. So this is essentially saying that one particular outcome, so let's say outcome A is better than outcome B because A provides unambiguously higher returns. So you're always getting a higher value in one outcome versus the other. And there is, for every value, for every input value, there's some probability of getting at least that in both of the variation of your inputs. And so I can actually graph this. So if I were to take this particular result and plot this out as a cumulative density function instead of a probability density function, so this is known as a PDF. You can calculate it here, and you can show that one outcome has stochastic dominance over another, which means that it's always going to be better. And so you can see that pretty clearly in this example. Okay, so let me describe what this plot is sort of showing. And actually, let me halt really quickly and make sure that everyone is at least comfortable with what this shows. Is there any confusion about this particular chart? Or is there anything that folks would like me to clarify? Nope, okay. So this chart is, I usually tend to find CDFs a little bit less intuitive, but let me explain. So let's think about just the red line for now, and we're just going to interpret this, forget all of the other colors. So if I were to take all of the outcomes from my Monte Carlo, I can stack them from sort of lowest to highest, in this case, expected value. And that is shown on the x-axis here. And so if I'm at an expected value of 0, essentially the count of total outcomes that are at 0 or lower is essentially this count here, and you can do it in terms of probability, right? And so let's say this is like, say 3% of the outcomes are at 0 or below. You can continue to sort of add in extra outcomes and going up the expected value up to, let's say here, this is, let's say this is about 1.25, right? So the number of outcomes with an expected value of 1.25 billion is about a quarter of the results, and lower. And so that's really sort of how you are interpreting this. And so right up here, kind of the highest is 5 billion or so. And once you're there, it's basically saying at this cumulative probability of 1, that all of your expected values are $5 billion or lower. And once you get there, you've encompassed basically all of your expected outcomes. So when you stack it like this, it basically gives you the probabilities that you are at a specific outcome. And if you see this sort of instance where you always have a non-overlapping line, so we're talking about the first offer, which is the red and the green, you can see that they never cross, which means that that declining the first offer, right, which is green, is always going to be higher than accepting that first offer, and that's known as stochastic dominance. This probably isn't the greatest example, but you can actually see that the lines cross here, and oftentimes, like in other types of problems, you know, they may cross more drastically and more sort of in the middle. But it just so happens in this particular example, the purple and teal lines do actually cross, and that means that that one outcome is not stochastically dominant over the other, which means that there is some sort of set of values at which the probabilities cross, and so we can't say that it's necessarily always better, because here you can see that there is some small area in which declining the second offer is, accepting the second offer is better than declining the second offer. And so in your second decision, you don't have stochastic dominance, while in the first decision, you do have stochastic dominance. Okay. So I'm going to go ahead to the next example, which is applying Monte Carlo to our insurance example. And so in this case, it's basically the same procedure here, where I've applied a couple of distributions to these parameters: the utility exponent, the probability of accident, and the accident cost. I have a triangular distribution here, and then normal distributions here. Again, these are, in this example, they're sort of completely arbitrary. Here, I'm not doing any overlapping distributions. These are outcomes that aren't really comparable. But here, looking at this, there is something to be said about simply the shape of the distribution, right? How wide it is, what are the range of values and likelihood of values. And so the shape of the distributions can help inform our answer, right? So for example, one of the things that if I were an insurance company that I want to look out for is, hey, it actually looks like under the conditions that we measured for the inputs, that we could have profits that are below 0, right? And while, you know, if you just measured the outcome without any sensitivity or uncertainty analysis, maybe you say, oh, it's positive, it's good, we should do this. But maybe when you include the uncertainty analysis, the fact that it's below 0 sometimes, that can be like an alarm bell for you, right? And again, you know, to reiterate and to reemphasize this point that like conducting the uncertainty analysis is enhancing your knowledge about the outcome, and looking, being as like an insurance company, being able to look at this diagram, you know, to me would be a lot more enlightening than, you know, just solving that decision tree once. Yeah, so it's really important to consider the range of possible values, the likelihood of those values that's represented right by the densities. Okay, one thing that that I'll discuss. So I don't have any like integrated examples of this, but it is important to remember or to consider that you can have systems where variables are connected with each other. And that means that your draws can essentially be correlated. And because the input distributions are correlated, the procedure that you take to do the sampling is going to be different. So for example, if you have 2 input distributions and you know, the second one depends on the first distribution, what you would do is to randomly draw from the first distribution and then figure out what the correlated draw is based off of that. The correlated second draw is based on the first draw. And one of the things to note is that correlated distributions often require a larger sampling size for your final Monte Carlo compared to independent distributions. Okay, so this is a point that I actually haven't really talked about yet. So let me go back actually. So for example, in this case, the number of draws that it is, I think it was about 10,000 draws from these distributions. And that's one of the most common questions that I get for folks who are doing Monte Carlo. It's like, okay, I've set everything up, and how many times should I draw, right? And you know, it's kind of similar to what I was showing before, like in the calculating pi example, right? I did 10, then 100. I was going up to like 10 million draws, and so there's this question of you know, how many draws is enough for the Monte Carlo? And unfortunately, there's no like straightforward answer, right? You can pretty easily see that the outcome distribution is not like a general type of application where I can just say, you know, X number of draws is needed. It's going to be very specific to the context of the problem, the complexity of it, the number of variables. As you draw from more and more variables, then the number of samples that you need increases, because the like combination of possibilities across variables needs to will increase as you add more variables. So there is no kind of straightforward answer. What I typically like to say is that you start with some low number of samples, make sure everything's working, and then you start scaling up in like orders of magnitude. And what you want from your sort of final result from your distribution that looks like this, for example, is like a fairly smooth distribution, which kind of represents the fact that you've captured all the sort of small variation and outcomes pretty nicely. And so if you have these really rough, weird looking distributions, then you tend to want to increase your sample size. And generally, not always, and I almost hesitate to say this because it really is context specific on the problem, but a lot of times when you do Monte Carlo distributions, your output distributions, right, this plot that you're looking at, those distributions tend to be normally distributed. And that's a function of the types of distributions that are feeding into it. You know, you could have multiple, like if your input distributions all were comprised of like triangular distributions, that doesn't mean that your output distribution is going to look like a triangular distribution. Oftentimes it'll just look like a normal distribution. But I will say that is not always the case. There are plenty of exceptions to that rule that, again, are dependent, are context dependent, and yeah, depend on the structure of the model. But yeah, the number of samples, basically keep increasing it until your output distributions look fairly smooth. Okay, jumping back ahead. Integrating uncertainty. So Monte Carlo is a process that can be integrated into basically all of the techniques that we've talked about so far. Okay, I ended up skipping our optimization lecture, but it's possible to, you know, run an optimization many times across different input parameters to get a whole slew of results that are based off of the optimization algorithm. And so, you know, instead of having the process being, you know, probability times cost, it's some like minimize or maximize problem, but you can still do that many times. And in fact, I have a student who's actually doing Monte Carlo on an optimization for looking at bus costs in Davis, for example. And so this is, you know, something that really, again, like a lot of this stuff can be really practically applied in your research. Decision trees, so we just went through a whole bunch of examples of that. You can even do this in, you know, regression or choice modeling, machine learning type of applications, where you use Monte Carlo in order to do things like prediction. One last thing that I'll quickly mention is you may have heard of a technique called bootstrapping. So these are pretty similar processes. Bootstrapping is and Monte Carlo are both types of simulations based on repetitive sampling. The distinction between these two is that Monte Carlo simulations are drawing from distributions based off of parameters that are known. In other words, if I have a uniform distribution, my parameters are min and max. If I have a triangular, it's min, max, and most likely. If it's a normal distribution, it's mean and standard deviation, and so on and so forth. So you are creating these distributions based off of parameters of the distribution that you either know or are defining. Bootstrapping is essentially the same thing, but instead of taking it from distributions that you create based off parameters, they are doing random draws from a sample of data. And that's either, you know, your population or available data. So you may have like real world data that has some like an event-based distribution, and you could just draw from that to do your simulation. And so these techniques are pretty closely related, very similar, but oftentimes, but they differ based off of what you know about the inputs. And the other thing that I'll say is sort of canonically, the types of problems that you do in bootstrapping versus Monte Carlo is oftentimes different. Monte Carlo is usually to, the application of Monte Carlo is typically to do, to capture uncertainty and show that in the outcomes of a particular model, whereas bootstrapping is more often like a statistical tool used to show like parameter values. But again, that's kind of at a high level and is a generalization. You know, the types of application for both of these techniques is has definitely broadened a lot. I would say even in the last like decade or 2 decades. Okay, and that is that mainly covers what I wanted to talk about with uncertainty and sensitivity analysis, and hopefully you guys can see some of the value in doing this type of analysis. And again, this type of stuff is really applicable to almost any quantitative modeling. And so hopefully you guys will find use for this in your own research. And it's something that I'm more than happy to help out with if you have any questions about it in the future. I'll end today with a slide showing application of this sort of uncertainty analysis in some of the work that I do. So this is examples of bootstrapping to look at charging profiles of electric vehicles. And so if I wanted to, for example, figure out what like a charging load distribution looks like for populations of electric vehicles, what do I actually need to know to figure that out? Let's see, I should know, you know, whether or not the vehicle charges today, how fast the vehicle charges, what time does the vehicle charge, and how much does the vehicle charge? So how much energy does it need, right? And all of these questions have different distributions associated with them. And these aren't like regular distributions that I was describing. Again, this is more from bootstrapping from real data. So I have the ability to look at whether or not someone charges today based off of survey data, right? And so, you know, for a particular type of vehicle, if it's charging at a specific rate, these are like the likelihood that it's going to charge in a given day. You know, for example, for DC fast charging, since plug-in hybrids don't have the ability to do that, for example, then they're both 0 across the full range, but then at level 1 or level 2 charging, there's some probability. At what rate does they charge? So if you have a different type of electric vehicle, you have a different probability of charging at these sort of different charging rates. What time of the day that you're charging depends on the type of charger that you're using, and so on and so forth. And so I can do this technique where I've set up distributions, or I'm bootstrapping from existing distributions. I can combine all of that through my algorithm or system model, and come up with these sort of distributions about what the load looks like at any sort of given hour in the day. And so again, this uncertainty analysis and techniques that you're getting from Monte Carlo and bootstrapping, really this really isn't kind of just like this theoretical thing that we learn in class. This is actually something that is really common in modeling analysis. And so, yeah, I definitely would encourage you guys to get comfortable with this because it can definitely be very useful in any sort of field of modeling. Okay, so that's it for today. I'll stop here and take questions for a couple minutes. Otherwise, I will see you guys all next Monday. Don't forget that the initial project proposals are going to be due next Friday. And so do make sure to reach out to me about ideas for the class project.